What's happening today? Not many in the class, probably. Is it because the previous class? And folks of those three groups should come on camera. Please let the others also in the group know. Okay, you'll be interacting with me today. Good. Okay, so would you have any questions? Would you have any questions? Ayush, Sharath, Shash, Vaibhav, Aditya, Sriraj. What happened to the others? Please, those three groups should have the camera on. So let me note it. Okay, we need to do something about this.
Yes, sir.
Folks, just let your group members know that they have to come on camera. Okay, let's observe something that we have promised. Okay, any questions you would have today? Any questions? Okay, so I have something on the board. So if just to recollect, we are looking at the strains now, right? That's what we started discussing last time. The strains as such can be written in terms of the changes that occur on two line elements, one along the x-axis, the other along the y-axis. These are small line elements that we take and find out how they change in their length, based on which we find out the strains epsilon XX, epsilon YY, and gamma XY, right? Gamma XY is nothing but the change in the angle as given over here, right? So if there is a change, there is a rotation that happens to the line element along X and line element along Y. We group them together and find out what changes occurred as far as the angle between the two line elements is concerned. And we use that information in order to find out gamma XY, right? In order to make it symmetric, we only look at change in angle, so that the rotation that would occur of the middle bisecting line, the rotation that could have occurred is removed so that I can get equal angles over here. And therefore, we will make an assumption that epsilon xy is equal to epsilon yx is equal to gamma xy v2. Okay, so far so good. Is this clear? And then we also said, okay, if we need the strains in the other directions, x prime, y prime, which is just rotated with respect to x, we can follow exactly the same thing that we did for stresses. The reason being, why is it that we follow the same thing?
Strain is tensor.
So the reason is because the strain is a tensor. I can use that transformation, which is to do with the tensor, and this is a second order tensor. Why second order tensor? Why is it? Yeah, it has two directions. But Karthik, you're not a part of the group here. It's a second, it has two directions and a magnitude. So, and magnitudes, and therefore it is a second order tensor. And we can use transformation law, the transformation law pertaining to second order tensor. Okay. This is what we learned in the last class. But we have no idea of what is the value of this epsilon XX given the change in the length. Okay, so that's the next exercise that we are going to do. If you have questions, you have to ask me now. Have you messaged your group mates? Okay. Let's look at what we did as far as finding strain for a one-dimensional body is concerned. Okay, this is something that we did earlier. So we will use that as the background when we go to two dimensions. What did we do? We had an axial member and it extended by a length delta L, original length being L. Okay, and let's say this is the x direction. We said, okay, if this is the case, then I can find out epsilon x. This pertains to the line element that is along the x-axis and its extension along the x direction to be equal to delta L by L. Another way of looking at it is, let us say I have a fixed frame of reference x and y. Let's say the initial configuration of the body is like this. The final configuration of the body is, let's say, something like this. And if I track the point P over here, which has moved to some other point here, and line element now has shifted, okay? The line element has shifted, not only shifted, but also elongated, okay? So we need to figure out how to do this. Let's just look at the one dimension first, understand it, and then go to two dimensions. Okay. So I'm going to draw a one-dimensional body here. Y has no role to play here. So I take a one-dimensional body. Okay. So if I take a point on this one-dimensional body and look at what happens to this point, let's say it is displaced. Let me use another. So let's say this is the initial point, this is the final point. Now it has displaced something like this, and this point P has moved to this point. Okay. It has not only displaced, but it has also elongated. So far, so good. Is this clear? Right. So what we do is, let's say this is the initial position. Okay. I'm going to use only X over here. Okay. This is the initial position X. Okay. I'm sorry. We are tracking the point P here. So the initial position of that point is X over here, right? What has happened? It has moved to a position over here, and therefore I'll call this as a displacement U. Okay. Now, after it has moved here, there is also an extension that has happened over here. There is a movement. There is also an extension. Okay. Just to make sure that we are on the right page, I'm just going to remove the initial part so that we start tracking only this P, point P. Are you with me? Just listen to me carefully. All right. Instead of taking the entire length, now let's take a small line element. A small line element. Okay. So let us say this is dx. Okay. What has happened is it has moved not only has it moved, but it also elongated. Correct? So what I'll do is I'll instead of taking this, I will now have an elongated length over here. Okay. And this is no more dx. It has now changed, right? The change has to do with how the displacement has occurred. All right. Are you with me so far? How the displacement has occurred. And how do I find out the change in this? The change in this has to do with how u has changed with respect to x. Do you understand this part of it? Or in other words, this could be taken as dou u by dou x times dx. Is this clear to you? So you have a dx and you have the changed one, which is dou u by dou x times dx, right? So if I take dou u by dou x dx and divide it by the original length dx, I should get epsilon x, which is now equal to dou u by dou x. Is this clear to you? Very simple idea. I'll expand this into two dimensions so that we can deal with two-dimensional relationship between what? Between the displacement that has occurred in the body and the strain. Questions? Yeah. Yes, Aditya.
Displacement doesn't mean displacement of the body method, it just means displacement of point P.
Displacement, come again?
Displacement means only displacement of P method, not the body.
Displace, so displacement of the left-hand side and the right-hand side I'm tracking now. Okay. Left-hand side I have put over here. There is a displacement of the left-hand. How this has changed, right? The displacement of the right-hand side over here. Here it is the same. The displacement, if there is a displacement that has occurred on the original body, the displacement of this point and this point is the same. Right? It is like a rigid body movement. But as far as this is concerned, there is not only rigid body movement, but there is also an extension that has occurred. Okay, and therefore we track that and find out what the strain is, because strain is not related to rigid body displacement, but only the elongation that has occurred in the line element. So far, so good. Is this clear? Okay. Any other question? Let's move to two dimensions now. Okay, let's move to dimensions. Why is it important to us? It is important to us because we want to track, we want to find out what is the strain in the body due to the displacement that has occurred of all the points in the body. So I can track, if this is the line element, I can track different points of the body and find out the strain in that body. Okay. So what will happen is I'll get epsilon XX as a function of x, where x has to do with the distance of each of these points. Each of these points, I can put it like this. Each of these points with respect to the original reference, right? This is the reference. Okay. So remember, the epsilon XX is also a field on the deformed body. Okay. The concept is very simple and clear when you look at one dimensions. Okay. One thing that we make sure here is we assume that the elongations that have occurred are small enough compared to the total length of the element. Okay. All right. With this idea, let's move to two dimensions. Okay. So I have a setup for you that I have done here. Are you able to see this? Yeah. So let's quickly understand this. Think of think of this to be attached to the original undeformed body. Okay. Let's say this whiteboard is the reference. Okay. With respect to the reference, this starts to move and also elongate. Okay. In both the directions, just like what we see was what we saw here. Okay. So this body, which was originally like this, moved and also elongated. Okay. Now what I'm doing is I'm tracking one point of this. I'm trying to understand what happens to the displacements. So far, so good. Any questions on this? Is this clear? Is this clear, Aditya?
Yes, sir.
Okay. Now, let me take the whiteboard. So I'm going to start with this. This is the initial position of a single point on this. So I'm going to locate one point and I'm drawing this. So this is point P. Okay, this point P has now moved to uh, a different place here. Okay, and what is this? What is this? What is this length? If I take only one square of this, what is this length of the line element?
1 unit.
Not 1 unit, but it is so small that I
Delta
take
x, delta x.
the delta x. All right, so this is delta x. Okay, so I'm going to say this is delta x. Similarly here, since I'm tracking two-dimensional, this is delta y. So far, okay? Okay. If this point has moved by a certain extent, and let me call that as u, this point, the same point has moved in the vertical direction by v. Okay. So far, so good. Is this clear? All right. So let's say this is x, this is y. So displacement has occurred of the point P, which is the starting of the line element delta x and delta y. So I'm going to call this as u and v. While I track the left hand side, it is displacement u and displacement v. But when I track the right hand side of this must be displacing differently compared to this point P. Why?
Because it's elongating also.
Because it is elongating. Very simple. That's what we did in the other exercise, right? So let's find out what would happen. So it has elongated now and it has also displaced. Okay. So definitely between this and this is not u. It has to be something else. What would that something else be? Let's use the continuity principle, like what we did there. Okay. It should be u plus the changes that has occurred in the displacement
du by
over
dx
delta x.
into del dx.
Right. So dou u by dou x times delta x. Right. This displacement. How about this displacement?
Dou u by dou y into
Dou u by,
dou y
okay.
into delta x.
Dou u by dou
Y.
dou what? Dou
U.
u by
Dou y.
into delta x. Fantastic. So in a similar way, I can do it for this point also, right? So this extension has to be v of the original point plus change that has occurred along the y direction times delta y, right? What else do I have to track? I have to track this, right? I have to track this, and this has to be equal to, help me out,
Only
help
by
me out.
only
Can't
by
hear you.
delta delta y.
Aditya, I'm not able to hear you.
Dou v by dou x into delta y.
Dou v by
Dou
variation
x
in the x direction times
delta y.
delta y. Very simple. All right. Now, is this enough for me to find out what would be epsilon XX, epsilon YY, and gamma XY? That's the question we are asking. What is gamma XY? The change in the angle, right? This is the angle which was initially pi by 2. Now it has changed, and therefore this is the angle that I'm trying to find out, from which I can find out gamma XY. Okay. In essence, it is nothing but this plus this, right? So let's go on to find out what it is. Let me take, is this side, okay, this side is visible, right? Okay. What is epsilon XX? That's the first question, right? Epsilon XX, I have to now look at how much extension has occurred here, subtract whatever movement that has occurred to P, right? So which is U plus dou U by dou X times delta X minus U, which will give me dou U by dou X times delta X. So it is dou U by dou X. Just a second. Dou U by dou X. Oh my God, this is also not writing. Epsilon XX is equal to dou U by dou X times delta X divided by the length of the line element, which is delta X, which gives me dou U by dou X, right? Similarly, epsilon YY is simple for me, which is nothing but dou V by dou Y. This is clear to you, right? Similar way I have to do V plus dou V by dou Y times delta Y minus V will give me the total elongation that has occurred here. And when I do that, I have a dou U by dou Y, dou V by dou Y times delta Y divided by delta Y, and that will give me dou V by dou Y. Okay. Can I write over here? What is now left out is gamma XY. Gamma XY, there is a moment that has occurred over here, and it has rotated. If I have to find out this rotation, that's very simple for me. I can take, for all practical purposes, this length to be delta X, divide this total movement that has occurred by delta X, and I'll get this angle 1. So it will be equal to 1 plus 2, right? That is equal to dou U by dou Y times delta X divided by delta X, right? That's the first one. So dou U by dou Y times delta X by delta X, all right? Plus the second one in a similar way, I have dou V by dou X times delta Y divided by delta Y, which will give me dou V by dou Y. I'm sorry, dou V by dou X. Okay, good. Now we have found out in terms of the displacement that has occurred in the body. Remember, this is only one single point I have taken of this entire body, right? I can do this for all the points of the body as long as I know what is the displacement field in the U and the V direction. Clear about it now? Okay. Any questions on this? It's a very, very simple idea. Okay. And remember, for all practical purposes, we have assumed that the elongations that have occurred are small enough. Okay. So that this dou u by dou u by dou x times delta x is very small compared to delta x. Questions? Mrityunjay, Sriraj, Shash, Sharath. If others have a question, you can ask through chat. Any questions? Jatin,
Basic, sir.
Vaibhav. Yes, Vaibhav.
No, sir.
Anybody who wants me to repeat what I've explained here? If not, no problem. So we have now uh, each one of these written in terms of displacements u and v. Okay. If gamma xy is in terms of u and v, gamma epsilon xx is in terms of u and v. I mean u, epsilon YY is in terms of v, which means that I now have a relationship between displacement and the strains. All right. So I'm going to go back to the board so that I can erase and use that form appropriately. Sir, while calculating displacement of x member along y, why didn't we add v to it? Oh, okay. Any of you in the video can answer that question? Chaitanya has asked, why didn't we add u to this and v to this? Quickly. Yes, Aditya, you said something. Others. Are you following? Somehow I'm seeing bare faces, so don't mistake me. The question is simple. Why didn't we, just like this, why didn't we add a U here? Why didn't we add a V here? That's the question that Chaitanya has asked. Chaitanya, you can answer by yourself.
I have an idea, but I'm not sure, sir.
Tell me what the idea is.
It's because it's a from initial position there will be an angle change. We're just finding that distance, but
Exactly.
in the diagram you have put the arrow from the previous diagram to the. That's why I have confusion.
Oh, okay. You're right. Thank you. Thank you. Thank you. Nice of you to make what you said is absolutely correct. Thanks, Chaitanya. It is actually this that I have drawn. In a similar way, it is this that I have drawn. Fantastic. Thank you. Thank you. Thank you. That's why this question. All right. So this distance and this distance are the ones that we are looking at. Else we would have added the original displacements also. You're absolutely correct. Thank you. All right. Any other question? Any other question? Very good. So let me just move on. Yeah.
Suppose you have only x component at this particular point.
Supposing
So supposing dou u by dou y is 0 at this point.
dou u by if dou u by dou y is 0,
and v is 0 at all cases.
v is 0, okay.
So then we will get linear response. If we have dou u by dou y, some small case, and then, but in the next immediate element, then v will become non-zero, right?
Yeah. But the thing is, this u is a function of p. This is pertaining to, so let me call it as up here. If that is going to give you an understanding.
So I was thinking if there is
The u and v are are displacements of every point in the body.
Yes, sir. So I was thinking if there is any way possible to have VP 0, but dou U by dou Y not 0.
Dou u by dou y non-zero and
VP 0 at all points.
at all points. No, but see, we are looking at the displacement with respect to the original point P, right? So let's just to draw, we had something like this. So let's say this is the reference axis. We had something like this. It has now gone to some other shape here. So this consists of one, which is a rigid body motion. The other is the elongations. Okay. Now, for every point, you will have these two displacements available. All right. For every point, because it's a field. It's a field of displacements that you would have seen. I compare that with the displacements of the original body. The comparison is what we have done in this for one single point with a line element which is an infinitesimally small element. That's the idea. Got it? So if I move to another point, it will have its own v and u of that x and that y. Just like I have x and y, this is with respect to the point P. If I move to another point, let's say an adjacent point, the adjacent point will have x plus delta x, y plus delta y.
No, sir, that was okay. That's fine.
Your question is not clear to me. If
So, like,
somebody
you
else has understood,
interdependent, sir.
u and v are,
Interdependent, sir. Like if we
why
change,
should they? No. U is displacement in the x direction, v is displacement in the y direction.
yes,
Those
sir,
are two independent displacements.
sir,
In a
but
rigid body also, it's a similar thing, no?
rigid body, you will be constant, sir. Like change will be 0. Rate of change.
Rate of change there is 0. Yes.
So if we
And
put
therefore, supposing it is a rigid body, let's say I have this and it has moved to this. Okay. What I have to do is I have to remove the rigid body displacement and only consider what elongation has happened. You understood what I'm saying? Which means that I have to now bring it back to the original position and do that. Okay. In a way, what I could have done is I could have moved this entire thing over here, right? So that the u and v disappear and look at only elongations.
yes, sir. But elongation itself depends on u and v, no, sir. I'm asking.
That's what. So what I have done over here is I have said that there is the rotation has been okay. Now I understood. Aditya, what you're asking is, well, it is like this. Now it has rotated also.
No,
So x
sir.
may not be.
Sir, no. Like if we,
I'm not able to understand your question.
like no, sir. If we arbitrarily choose a function u, so that it is only a function of x and not y.
No, x and y.
No, sir. Like we are choosing it. We are fixing it like that.
Oh, we are fixing it like that. Okay.
We are taking a material like that, and then is it possible to get a non-zero VP?
Non-zero VP. If there is a rigid body movement, yes. If there is no rigid body movement, you are talking about just one-dimensional elongation. Is that what you are saying?
Something like that.
Yeah, one-dimensional elongation is possible in this also, where dou v by dou y is equal to 0. In this case, dou u by dou y is also equal to 0. So there is no shear, there is no y strain, you get only x strain over. It is still consistent.
Yes, sir.
Okay. All right.
But sir, in a practical body, is it possible, like if we extend it along one direction, the other will also compress?
We are talking about a one-dimensional elongation. Am I right? Yes or no?
Yes, yes. One
Yeah.
dimension is possible. I mean, in a two-dimensional body, if in practical case, if we extend it along one direction, it will compress along the other
Oh,
direction.
no. Don't get confused with this compression and all those. If there is a if there is a contraction, then there is a V displacement also. In which case you will get a strain in the Y direction also. You understood? Supposing I have like this, okay, and then it has now elongated like this without change in this breadth, then it is only X elongation. But if it has changed like this, there is also this contraction. It is no more one single direction. There is also the change in elongation. I'm sorry, elongation in the Y direction, where epsilon YY will also come into picture. If that's what you're asking, that's the reason why you're asking is you're now visualizing a material that is being pulled. It is also getting contracted in the other direction, and therefore this confusion. The confusion is very simple. If you look at mathematically and they'll say there's no change in the breadth, then it is only one dimensional strain that you will get. But if there is contraction, then the second dimensional strain also will come into picture. So in this case, I will have epsilon XX as well as epsilon YY coming into picture. All right.
Yes.
Since the angles have not changed, gamma XI will be 0. So far, so good?
Just one more doubt, sir.
Yes.
How are we accounting for rotation? In our calculation, we didn't.
Okay. So what we did was this. Sorry, I'm just going back and forth. What we did was this. When we changed, when this has rotated and this has rotated, not necessary that we have one need not be equal to 2. Right? What happens basically is if I take a bisector, which is 45 degrees here,
Not this rotation, sir. Rigid body rotation.
this one. Initially it was pi by 4.
Hmm.
This angle with respect to horizontal need not be pi by 4. There is a rotation that has occurred.
Okay.
That's a rigid body rotation. So I have to remove that rigid body rotation, and therefore I'm taking 1 plus 2 as the total change in the angle,
Okay.
where rigid body rotation is taken care of. Good question.
So observer is on the body or something like that.
Come again?
For the axis, like XP, YP, it is not with respect to ground. It is.
Aditya, you're speaking as if it is from. We hear it as if we are speaking from a well.
Uh,
So I'm trying to figure out what you're saying. Maybe a little louder.
Sir, like the XP, YP, it's not with respect to ground, sir, and it is with respect to the coordinate axis.
XP. No. What I'm saying is there is an absolute axis. There is an absolute axis with respect to which I'm tracking this point P.
But if there is an absolute axis, then that pi by 4 will remain pi by 4. Sir.
No. See, the body has rotated. So the body was like this. It has rotated a little bit because of this. Because of the shearing, it has rotated a little bit. So I want to remove that rigid body rotation. By how do I remove that rigid body rotation? By taking these two to be the summation and divide it by 2. Right? If you look at it if I symmetrize this and this to be the same, what I have done is essentially I have taken care of this rotation. You can do that calculation. Okay, one is 1 minus 2, the other is 1 plus 2. 1 minus 2 by 2 and 1 plus 2 by 2. The total put together will give you 1 and 2. Okay.
Okay, sir.
Geometrically.
Okay, sir.
So deformation could cause rotation in the infinitesimal body, infinitesimal point of the body. Okay, and I should remove that rigid body rotation in order to do this. But all these calculations are for small deformations. Okay, that's the idea. Okay. For large deformations, we have to do slightly differently. Take the advanced course, I'll teach you what it is. Or probably separately, I'll be able to teach you. Okay. All right. Let me move on now. Let me move on. So, where is that? So, what we found was epsilon XX is equal to dou E by dou X. Epsilon YY is equal to dou E by dou Y. And gamma XY is equal to dou U by dou Y plus dou V by dou X. Is this visible? Yeah. Okay. Now, I have taken in such a way that this 1 and 2 of the angles that we have, we made them equal by slight rotation that has already occurred, which means that epsilon xy is half of gamma xy. It is also equal to yx. So we did a symmetrization. In the last class, we discussed this also, right? So I have now dou u by dou x, dou v by dou y, and this. Let's take x to be 1, y to be 2, u to be u1, and v to be u2. Okay. So we will have epsilon 1 is equal to u1, comma 1. What is this comma about? What is this comma? What is this comma that I have introduced? We did this exercise last time. Derivative. It's a derivative with respect to x1, which is x here, right? Similarly, epsilon 2 is equal to v. Should I write v here? Should I write v here?
u2.
It is u2, comma 2, right? Are you with me? How about epsilon 1, 2? Half of
u21 by 2.
half of
u12 plus u21.
u1 comma 2 plus u2 comma 1. Agreed? Yeah. I can write this to be half of u1 comma 1 plus u1 comma 1. Can I not? It's the same. Similarly, I can write this to be half of u2 comma 2 comma plus u2 comma 2. Yes. All right. Why I have done that is I want to see the similarity here. I have a 1, 2 here. I have a 1, 2 over here. So that in all this, I can now simplify and write anybody epsilon ij is equal to u. Somebody is not very audible.
Half of uy.
Half of fantastic. Half of
uij plus uji.
uij plus
uji.
epsilon ij is equal to half of uij, sorry, I comma j plus uj comma I. Okay, where I is equal to 1 comma 2, j equal to 1 comma 2, right? So it's a very simple form that we have written. How do I now extend this to 3 dimensions? How do I extend it to 3 dimensions?
1 by 3.
You add a 3 over here and you add a 3 over here. Over. Simple. Okay. Just to be specific, it is for small deformations. Would you have any questions related to this? Very simple ideas that we are looking at. Okay. It can be made as complicated as possible, but right now we are just making it as simple as possible for us to understand, especially for small deformations. Yes, Sriraj? Okay. Now, let me go back now. We have this equation that we have established. We also established an equation, a differential equation in terms of stresses through equilibrium, right? So we had stresses, we used equilibrium principle, right? And wrote down 3 equations. What are the 3 equations? What are the 3 equations? Sigma ij comma j plus bi equal to 0, I is equal to 1 comma 2. So 2 equations. Correct? 2-dimensional 2 equations, right? And how many quantities did we have? Sigma 1 1, sigma 2 2, and how many quantities did we have? How many unknowns? 3, right? So unknowns, 3 of them. Okay. So I cannot solve for the unknowns unless one of them is naturally equal to 0, right? So that's the reason why we need to go resort to strains now. So let's look at strains. Strains, what did we use? What condition did we use? What condition? Go ahead. That the displacements are CONTI continuous and differentiable, right? So it is the continuity of, right? We introduced continuity for strains in order to get this. How many equations have we written now? Here? 3 equations, right? So epsilon ij equals half of u comma I plus uj comma I, right? And this is 3 equations. And how many unknown quantities do we have here? How many unknown quantities do we have now? 2 displacements and 2 displacements here and strain 3. So 2 plus 3. Correct? This is displacements u comma v, and this is epsilon 1 1, epsilon 2 2, and gamma 1 2. Right. Again, if you look at the total here, I have 5 plus 3 8 equations that I have to I'm sorry, 8 unknowns that I have to solve for, but I have only 5 equations that I've generated so far, which means that I'm short by
3.
3 equations. I need to get 3 more equations. Once I get 3 more equations, then I'll be complete along with the boundary conditions. Are you with me? Right? Where do we get those 3 equations? That's the other question, right? Where do we get the other 3 equations? We have already exhausted equilibrium. We have already exhausted continuity. The only other thing that is left out is the relationship between stress and strain that is provided by the material, right? We initially talked about how materials are different in nature from each other. One is soft, the other is hard, etc., etc., etc. And we need to build that into the set of equations, okay? And that comes from the material, right? Okay. We usually call this as constitutive equation, or we also call it as material law, or we just say stress strain relationships. So it relates basically stress and strains, and we will look at how many equations we can generate, what kind of equations they are, and see whether there is a tally between number of equations and number of unknowns. Okay. Once that is done, I have all the equations that are necessary for me to solve for any body subjected to any force. Okay, as long as I can solve the differential equations that is on the board. Is this clear? We are now making a completion in terms of what all do we need and what all do we have, and see if we can solve for the displacement field, this displacement field, the stress field, the strain field in the body. Okay, so given a body, if I ask you the question, what is u of x comma y, what is v of x comma y, what is epsilon ij of x comma y, and what is sigma ij of x comma y, you give me these 3 equations plus those 2 equations, I'll be able to solve for them. Okay, that's the next. So we'll do this and look at all the equations put together to see if we have complete set of equations to solve for. The same similar stuff it can be adopted for 3 dimensions also. Okay, this will become 3, this will become 6, and so on. Okay.
So why isn't BIA available?
What is BI is a body force. Body force is an external force. Okay. Good. Thanks, folks. We'll some question is there. 1 second. Shouldn't 1 be dv by dx times delta x? No, I need to have a look at it more carefully. In the video, you will understand. Okay. Why didn't we add? Okay, that I have answered. Any other question you have? Any other question? Very good. Thanks a lot, folks. We'll meet tomorrow. Okay. Please go through this video. And Chaitanya's question was pertinent. I made a mistake over there. He corrected me. Thank you. All right. Bye.
Thank you, sir.